This is my presentation on how to determine the seasonal weather. In this particular case, it's rain, and it's rain for Lake Charles, Louisiana, just like we did on the rain delay. The big difference here is that we're actually going to try to calculate from the hourly data our P10s and P90s, our mins and maxes, as opposed to what we did with rain delay, where we arbitrarily assign a plus or minus 2 days to the min and the max. Now, it seems like that was not a bad approximation, and I would probably recommend that or some variant of that as opposed to what we're going to do here. The data manipulation here, data analysis here, is fairly onerous, fairly tedious, and so unless it becomes very important for you to know what your mins and maxes are, I would probably stay with the plus or minus whatever factor you want to use. Now, like I said before, what we're going to do is go to the actual NOAA hourly data. In this case, it's going to be from 1962 to 2011, approximately a 50-year period. And from this data, we're going to then construct our weather calendar. Now, what we did in rain delay before was take the average data for, and we used the weather base for that, for rainfall in excess of 0.20 of an inch, or 0.2 inches. And we're going to use that same metric, though I'm beginning to believe that we could reduce that to 0.1 inches to determine a rain day, though that is still indeterminate. Several different mechanisms are used. One is a circle on the ground or a brick, and then the number of raindrops in a particular period of time, generally a minute. Not altogether empirical and highly subjective, actually, because it varies from superintendent to superintendent. But we had to have a point to start with, and I stayed with the 0.2 of an inch. And what we're going to do here is take this data, analyze it, the assumption being that it's normal, and I'll show you that in a little bit. I think that's a reasonable assumption, especially given the fact that we've got a 50-year period here. But we're going back again. The situation is we need to convert hourly data into probable non-work days. And the major departure that we're going to do here between what we did with rain delay and what we're calling seasonal weather is we're actually going to try to determine the P10s and P90s. Now, for rain delay, what we did is just arbitrarily select a plus or minus 2 days. Now, that did turn out to be a reasonable approximation, and I would probably stay with that under most circumstances, because what we're going to do is fairly difficult, arduous, I should say, not difficult, because it's a lot of data manipulation. So what this is really going to deal with here on the seasonal weather, the big departure here, is how do we get to the P10s and P90s for our weather calendar. And once we create the weather calendar using the hourly data, and we're still going to allow for the same makeup Saturday, and then we're going to create a weather resource. Now we're not doing anything differently than what we did in the rain delay. The big difference here again is that we're actually going to try to determine the P10, the min and the max, using data analysis. So we're going to create the weather calendar as a resource for all affected activities in P6, add the weather calendar, the schedule, and then perform the analysis. Okay, this is where it starts. This is where we get our raw data, and nothing magical here. Just this seems to be the best source right now for what we want to do. It's a little involved, but the data is free. So if we were to look at the raw data, it looks something like this. Now I have changed basically columns B, C, and D so I could do some sorts on this thing. And this just gives you some idea of what we're looking at here. Just did some analysis here. Just an attempt to at least visually to validate that we're talking about normal data. So interestingly enough, these are the daily totals in a particular month for a rainfall in Lake Charles over this 50-year period. And so it averages out to about 9 inches a day. Don't know where you want to do with that, but anyhow, and our standard deviation is only about 1.2 inches, so about 14% of that. So it seems to be a fairly nice bit of data. So once we have that, then the key becomes to convert that into something that becomes useful. So here's a pivot table that I did, and what I'm trying to do here is just do a sum on the amount of rain in excess of 0.2 of an inch, or 0.2 of an inch. And so this is what we get for the month of December. And these are the various dates that are there. And then this can be, for me, was a manual thing. I'm just going through and counting up the number of days. And then with that, all the way through until we basically are able now to come up with the worksheet here. So these are, again, the number of days that I counted by year, and just determine the mean on that, the standard deviation. From that, I got then the P10 and P90. I used a z-score of 1.28 to determine my P10 and P90s. So then I just have this particular table here, rounding off to whole days, of course. And then that allows me to construct my table. Now we're doing something pretty close to what we did before with rain delays. The difference here is, instead of doing plus or minus 2 days, we are actually calculating the number of the P10, the min and the max, using now the subtracting the number of Saturdays in that particular month. And so then we get the output here, and then from this output we now have our normal table. This is, at this point now forward, it's going to be exactly what we did for rain delay. But I'll just back up a little bit and show you what we did in this thing here, coming from our raw data, and then just doing a pivot table on that to get the number of days in a particular year in which we had rain in excess of 0.2 of an inch. And then just counting up those numbers of days, turning that into this particular table here, which is again the number of days in that particular month, in that particular year, in which we had rain in excess of 0.2 of an inch. And then summing all of that, of course, and getting our mean, and then getting our standard deviation, and then from that using a z-score of 1.28, coming up with a P90 and a P10, which then rounding off gives me this particular data here. Now this is going to be our standard annual experience here, and the only difference here now is that we're going to have different Saturdays in any particular year. So, and I'm doing again the 2013 through the 2020. You've seen this before. I won't spend any more time on this, but this is what we want to end up with. We've got to come back to our weather calendar. And so this is the weather calendar. Obviously, I've removed any negative values here. It will cause, as you might expect, it will cause uncold pain within PRA Master. Yep. this is our results. Nothing particularly unusual here. Variation is 20 here, which for a 4-year schedule is not terribly impressive. It should be noted that with the weather-based data, our variation was 35. But I think there's some problems with the weather-based data, and maybe this causes into to question what we use as our data. If you notice, here's this kind of a summary of our the NOAA-derived data, and I don't know if you can tell this too well, but it looks like instead of the plus or minus 2, plus or minus 3 might have been a better approximation of what's going on here. Now, of course, you don't know that until after we've done the review, but it's just something to keep in mind that your standard deviation here, or the Z, is going to be somewhere between 2 and 3 days thereabouts, and then it's just your call as to which you think is most important. But what I want to call to your attention here is this is a summary of the means of the weather-based data and the NOAA data, and you can see that we really have a variance here, a fairly significant variance. In this particular case, it's 30 days, or approximately 80% of our NOAA data. So, and this occurs in a couple of different places here. We got a variance here of 11, and another variance here of 5 and 5. Other than that, things look pretty good. Talking to the people at WeatherBase, there may be some problems with the way that they're reporting their data, and they warned me about this before. And so I just call it to your attention that be careful of what you use in the form of data. But this gives you a way to handle a great deal of data. And again, this is where the pivot tables just really shine. If you're not familiar with how to use them, I suggest you get some data, some experience, because they can make handling a lot of data. Here you can see we almost have 26,000 cells, rows, and pivot tables just make handy work of that. Well, I hope this has been helpful, and hopefully you can use this for other things. And again, this should work with snow, should work for temperatures, should work for almost anything for which you can find data. So, any questions, give me a call. Thank you.